Okay, with that mask faux pas behind me, thank you very much. I'm supposed to be the one reminding you guys to wear your mask, not the other way around. Hey, we got a Robotics 101 t-shirt in the classroom. I was going to wear mine and I forgot that too this morning, so life has been hard. We're starting a brand new topic, optimization. And what we're going to see that there are certain engineering problems that we can't just pose as finding a solution of an equation. Okay, it makes much more sense to try to minimize the distance from where you are to where you want to be, sort of like we did with least squares, but this will be a generalized notion of distance. How close can we get to an answer that we think is ideal? So that's what optimization would allow us to do. My sincere desire is that you come out of the course thinking that this crazy function argmin, oh, come on, go back, is just as good a function as sine and cosine and exponential and x squared. So the fact that you take a function and what argmin does is returns a value of the function where it takes on a minimum, that becomes something that you appreciate as an operation, just like, once again, computing some other value, whether it's exponential, log, or whatever. I want it to kind of become an ingrained notion that argmin, similarly argmax, the opposite, are just functions. They're really complicated functions, as we'll see, but they are functions. And if we can find algorithms that help us determine the values of x that achieve the minimum, that's a really marvelous thing. We'll relate the notion of a derivative to the existence of extrema. So extreme points are minimums, maximums, and then these kind of saddle things if you have x cubed coming in. But we'll just talk about minima mostly. And then the other stuff that's on there is maybe too advanced for what we're doing today, but towards the end of the chapter, they'll make more sense. So we'll save them for then. So here's going to be my way of posing a problem that at least I don't know how to set up as find x that satisfies g of x equals 0 or something like that. So here's the sensor package on Cassie. So you see the LiDAR, so that's the same sensor that generated the data that you used in Project 1. What you didn't have available to you were the camera images that were also being collected at the same time. Okay, and we won't worry about the motion capture marker for this presentation. So Cassie has two ways of sensing data. One, the camera image, and the other, the LiDAR. So cameras are wonderful today. They have millions of pixels. So pixel just means camera element. It's the little bitty tiny dot that an electronic chip is collecting where it's getting you the wavelengths of light that are hitting it and giving you an RGB, red, green, blue value, okay? And they're extremely dense these days. So the original digital photographs were really large pixels and they looked horrible, and today they're just little bitty tiny things. So we have megapixel cameras in commercial phones. It's just incredible. So the density of data you get out of a camera is really great. But what a camera can't do very well is tell you how far away I am from you. It can pick out your shape, your color, all these beautiful things, so it's great information, but how far away is that clock? It's terrible at that. what a LiDAR is really good at, it's sending out these laser beams. And so light goes out, it reflects back, we measure the time it takes to reflect. We know the speed of light, so we know the distance. So it's super good at distance. But the data is rather sparse, meaning we're out in an area where I might have 10,000 camera pixels in this, I might only have 100 dots from the laser. Okay? So the amount of LiDAR data that I get in any particular image is much less precise in terms of the granularity of spatial resolution, because maybe I get 3 dots on that chair, okay? Whereas with a camera, I will have hundreds of thousands of pixels returned. So we like to use both when we can. So we like to merge the data into something like this. Oops, get back in there. So this is a camera image with the LiDAR data overlaying. So what do we see? Well, we see this geometric object called a curb on a sidewalk, and we can tell that the LiDAR is really well aligned because you can see that there's a distance drop-off as the LiDAR goes across. So it's aligned perfectly, really. It's really gorgeous. Now, once again, sparsity. Look at all of the information in between the LiDAR beams that we're missing. So we don't want to use just the LiDAR. We want to use the camera, but we want to use the LiDAR really to give us the distance to something. And then the camera, we can use that to tell whether it's sidewalk or grass and things. We get textual information about what's in the scene so we can interpret it and decide how to navigate. Now, here's the problem. You just mount a LiDAR on your robot and you mount a camera on your robot and you compare the two things. You're lucky if it comes out this close in the beginning, okay? So here, this is the curb. You see where the LiDAR thinks the curb is. That's not good, right? So you're trying to build a map with this beautiful techniques that you guys saw in the first project, and then you start walking based upon that, and it's not aligned up with reality. So what's the problem is the coordinates of the camera are not the same as the coordinates of the LiDAR. Remember, each sensor, it doesn't know about anybody else's sensor. It measures with respect to its own coordinate system. It has its X, Y, Z. Okay, so if you want to take this data and overlay it with that one, you need the transformation that takes something from this perspective and moves it to as if you were looking from this other perspective. That's called calibration. As soon as I mount these things rigidly to the robot, they don't move. But the thing is, when I mounted them, nobody told me what that transformation is. The manufacturer of the LiDAR is not going to tell me the transformation to the camera because they don't know where I put the camera, and vice versa. So we have to, from data, determine the transformation from the LiDAR to the camera, and that process is called calibration. So this is not aligned. And so how would you pose the problem of finding the rotation and translation, the rigid body transformations that you were using in Project 1 that takes the LiDAR data and snaps it onto the camera data? Well, what you would maybe like to do is minimize the distance from these types of features to those types of features. Okay? So on Wednesday, my student Bruce, who achieved this beautiful calibration, will come and tell you how he actually does it, and it's using optimization. So he'll show you, in just 15 minutes, roughly what's going on, and then you can read the paper if you want more, or What we're hoping by exposing you to these types of techniques and problems is that you'll use that as you're selecting courses to go on if you find parts that are super interesting to you. So optimization is, you can think about it as one great use is minimizing the error in the LiDAR image overlaying on the camera image. But what does it mean to have a distance between those? That's where good engineering comes on. And then once you know what it means that to be well aligned, and poorly aligned, how do you achieve the rotations and translations to do that? That's an optimization problem. Okay, so that's the motivation I'm going to use for, why optimization is important. It allows you to solve really cool problems. Okay, so I'll just use the images to motivate that. But then let's talk a little bit about just what is optimization when you start trying to make it a technical thing that you can study. Okay, so it has a few ingredients. So we have to start out with a set of potential solutions to a problem we care about. That seems pretty vague. But if we go back to this thing, it's the set of rotations and translations in 3D space. That's what we're looking for, okay? So we'd have to write down a description of the set of rotation matrices we can apply in 3D. The translation, that's easy. It's the rotations that are hard. Okay? So for the LiDAR camera calibration problem, this would be the set of rotation matrices and translation vectors in R3. So turns out that's a really complicated set. Doesn't sound complicated maybe on the surface, but when you start digging into it, it is. We will assume, because we're just doing an introduction to the subject, our set of possible solutions is Rm for some m, okay? We'll call it Rn, that's fine. Rm. And it's kind of nice to be at a point in the course where now the set of all column vectors seems like an easy thing, okay? Remember back when that was like, oh, it's so confusing. I want to stick with the real numbers. I get it, okay? But compared to other things in life, that's pretty good. So that's the first thing we need is a set of potential solutions, the thing we were trying to find. So calibration its rotation matrices, etc. Then we need a way to distinguish amongst solutions. What is good and bad? Whoops. Qualitatively, good solutions versus bad solutions. Oops. Okay, so we will do that with what's called a cost function. So we'll take some function f maps our potential solutions and assigns to it a real number. Okay, called a cost function. Okay, so the cost function allows us to compare two solutions and say which one we prefer. Yeah, it's cost, kind of like money. So a lot of this optimization stuff came out of economics and things. But you go into a store, do you want the most expensive item or the least expensive item? And it kind of depends. Well, more expensive, that sounds like more luxurious. I like that, okay? And other was going like, more expensive, that means I can't have as much money for Friday night as I would like to have, okay? So it depends on what you're doing, what the cost means, okay? So if you're trying to minimize the cost, so looking at the least possible cost, that's minimization. And then the most cost, I guess, that's maximization. Okay, so they're just both forms of optimization. You can try to make the cost as small as possible or big as possible. They're essentially the same problem. Just some information that provides nothing technically, but a little bit of the spirit of science, okay? So in the branch of artificial intelligence called machine learning, one uses rather folksy and I would say fun vocabulary. So if they take a cost function, remember, it's just assigning real numbers to all of our potential solutions. It's called regret. I should have written that in red. I'll underline it since I didn't do that. Regret, when you're minimizing the function, so if you go to a seminar, and there's a lot of seminars in campus. Now they're mostly on Zoom, but if you hear somebody talking about minimizing regret, now they just pose the cost function and they just call it regret because everybody wants to minimize their regret on the solution, right? You don't try to maximize how much displeasure you have with a particular solution. They call it regret, which is kind of cool. And then F is called, and I will get this one in red, a reward when doing maximization. I don't know. Okay, because everybody wants to maximize their reward if they can. Okay, so that's just, you'll hear it so much, and at the beginning it sounds kind of confusing, and you realize they're just talking about a cost function. Okay, so optimization is somebody somehow magically gives you a cost function, and you're seeking values in the solution set that either make it small or make it large. So that's optimization. Okay, now, designing cost functions for a problem is absolutely typically the hardest part of the problem, okay? So that's where the engineering comes in. And if we just go back to the LiDAR and camera, how do I measure the error in how one thing overlays the other? Because for a particular laser point and a particular pixel, there's nothing in those pixels saying that this is a curb side and that this is a curb side and that they should correspond to the same 3D point, okay? That is super, super not obvious from the data what it means that these two things are aligned, okay? So it's a very holistic problem, and that is real engineering. It takes a lot of experience in reading the literature to see what people have tried, and then you trying something new if the solutions in the literature are not working very well for you, okay? So it takes a lot of practice. Okay, so we will assume has been given to us and work on algorithms to find a minimum. It's already a pretty good thing to be doing. And I say minima, the plural of minimum, because often there's not just one, okay, to find minima of functions. Okay, so that's, okay, how easy is that? Well, share with you some images that Professor Ghaffari put me onto. Let's start with this one. Get out of the way. Okay. So this is someone's kind of imagined landscape of what a typical machine learning algorithm in artificial intelligence is trying to do. Here's your cost function. This is how irregular it is. Okay, you're supposed to be thinking about it spatially, but really there's maybe 10,000 dimensions. Or if you're Google's recent deep learning algorithm they've released, which is generating natural speech to write about topics, it's literally billions of different parameters, and each parameter is a dimension, okay? Can you see a billion dimensions? No, but you can comprehend that it's complex, okay? Now, here's the minima. So here's our cost function, and let's suppose we're trying to find a minima. Where do we move to go towards the minimum, okay? So we could maybe slide down into here if we had an algorithm to kind of descend the cost values. Maybe if we're lucky, we would start, and it looks like there's something really promising in there. But look, it's so easy that you start, and then you start going up, and so you say here, and you have no idea that there's a really much better minima that's nearby. You can't see it because nobody's giving you this picture because it's really in R 5,000 at a minimum, okay? So cost functions can be horrible if they're posed incorrectly. And so a lot of the work please. Oh, you're here. Thank you. Let's do this one. Now, what this paper was trying to talk about is this is the cost function this author's competitors were using and how the parameter landscape looked, whereas this author found a different cost function where they both, of course, identify the right point, okay? But it's much easier to start not at the minimum with this cost function and find an algorithm that finds its way down to this local minimum than it is over here, okay? So I'm just trying to give you the qualitative understanding that someone who's giving you a cost function, is it this one? You're the numerical person, or is it this one? Okay, and if no one's found this one for the problem you're working on, does it exist? That's a research area, trying to find good cost functions, okay? Just give you an idea where the engineering or applied mathematical work needs to be done. Okay. Let me show you the type of cost functions we want to start out with. Okay. So this is illustrating local versus global minima. Okay, so after I've frightened the death out of you with what some of those cost functions look like in deep learning and things, let's go back and say, look, we are newbies, we're just getting started, we want to like figure out what's going on. And believe me, I'm much closer to this level of optimization than I am what I was showing you in terms of what the high-end machine learning people are doing. That is not my area of expertise. I use it, but I don't develop new results in it. So this function is really simple, and it's clear, whoops, if this is the function, that there's a global minimum. If this is truly the function, it just keeps growing, it's quadratic. Okay, so this is a single global minimum. Whereas this function has, yeah, that looks like it's a global minimum, but looks like it has a single global minimum. We're lucky. But they're both local minimum. Oh my gosh. Local minima. Get out of there. Okay, and then it has a local maximum, and then apparently the global maximums are at plus infinity and minus infinity. Okay, so it has extrema way out there. So this is a local max. So the local means here, if I just look in this region, it is the smallest value in that region. Okay, that's what local means. Smallest value in a small region. Local minimum equals smallest value in typically a small region. Okay. So what we often face when we're doing optimization, this would be like the dream situation because there's only a single one, but often, we don't know because we haven't explored the entire solution space. It may be very large, but it will have these local minima, and you could easily be at a local maximum as well. Okay, so those are the challenges. Okay. Our goal is we want to find x star equals argmin of our cost function over our set of potential solutions. Now, I don't know if you've heard of this expression before, abuse of notation. Okay, so when I write down a point and an equal sign, hey, that's a point. That is not a set. Okay, it's not a set. So what if my cost function looks like this? It's perfectly flat. Okay, so cost. Okay. This whole set, entire set, of minima. Now, once again, I've got a problem, I've posed a cost function, and then I say, this is what I'm looking for, but really, this could be the situation. It's not a point, but a whole set. This notation is actually wrong, but it is so commonly used because it speaks to what you're trying to do that everybody always writes this down, okay? And on a given problem, the amount of analysis you would have to do ahead of time to assert that you're in this case, there is only one point, so it is really a point and not a set, is so hard that you can never do it before you start solving the optimization problem. Okay, so you just can't determine ahead of time whether this is even correct notation. So what people do is they punt, and it's called abusive notation because it's not correct, but yet it says what you're trying to do, so people use it anyway. So really, you should only use this if you know that this is the type of cost function you have, but proving that is so hard because even here, you start with, in this area, you'll find this one. I start in this area, I'll find that one. And our solutions don't agree, okay? So it's abusive notation. So we will use that abusive notation because everybody does. Okay, now let me insert. This mask is getting in my eyes, and so that's going to remind me never to forget my mask, my own mask. Okay. Okay, you're done. Close. Boom. Okay, this plot tells us our basic strategy for optimization. I'll do a little bit more analysis so that we're not just living with the picture, but okay. What I did was I took our simple cost function and one that's a little bit less simple, and I plotted the slopes at various key points. Well, here's a point. So these are just lines, and the magnitude doesn't really mean that much of what these lines are, okay? There's a slope, there's a slope. So these are the derivatives of the function at various points. And so the first observation we have for finding local extrema, and we'll just mostly talk about minima, is that look at the slope at this minimum. The slope is 0, okay? Same here, the slope is 0. I just computed it. Now, it's the same at a local max too, okay? So the derivative doesn't tell you everything, but here, the slope is say 1 or something. That is not a local minima nor a local maxima. So derivatives vanishing, derivative vanishes as our first observation. Equals 0 at local minima and maxima, plural of maximum. Okay. So we'll go to our linear approximations and do a little bit of analysis work to really say that, wow, that's just those two pictures, yeah, maybe they were lying to me because they were just avoiding some things that are really important. Okay. Here's the next thing, though. So, and the simplicity of it is going to blow you away, I think. Okay, so Let's suppose I'm working near this particular local minima, and I start here. Which direction should I move to go towards the minima? Now, what you have to imagine is you don't see the function, right? If you already had the complete description of the function and all of its many dimensions, you would just read off the minimum and you're done. You don't do any algorithm, okay? You do it by inspection. So all you know is what's happening here, and you're trying to decide, do I move this way with X or do I move this way with X, right? I'm in R, I've only got two directions to go, or I just stay put. So the derivative here is positive. What does that mean? If I move to the right, the function is growing because this is rise over run. The derivative is positive, so the slope is positive. If I go to the right, the function is increasing. Is that towards the direction of a minimum? And the answer is, it's the opposite direction, okay? Oh, can you make that point any more forceful, Grizzle? Okay. Just because I've got a better picture over here, I'm going to move my focus to this one. And now I'm looking to the left. Here's my slope. The slope is negative. Rise over run. If I move to the right from this point, the slope is downwards. So when I go to the right, I'm decreasing. I'm moving to smaller values of the function. That's what I'm trying to achieve if I'm doing minimization. Whereas if I move in this direction, which is the sign of the derivative, I'm moving away from the local minima. The derivative points in the direction in which the function is growing. Okay, this is a super hard concept to get into your head maybe initially because you don't think of derivatives as pointing, but I'll do it this way. Derivative indicates in which direction the function is increasing. df dx at some point positive implies increasing the function, increasing to the right. And df by dx negative implies increasing to the left. Okay, I'll let you write that down and we'll go to our pictures. And then I want to use the linear approximation of a function to just make all that stuff rigorous, okay? But here it is once again, rise over run, the slope is positive, so that means that this point was higher than this point if I move in that direction, okay? And here, rise over run is negative, so if I start here and I move to the right, this value is less than, that's what the slope being negative means, and so I would decrease in this direction and increase in this direction. The same here, I increase in that direction and decrease in this direction. The sign of the derivative tells me what to do, and if the derivative is 0, then I get no information about growing in either direction. It looks like the function is flat, and we're at a local max or min. Okay. Okay, analytical view. Well, let's just write f at x equals, this is the x at which I'm living. Just like when we did Newton-Raphson, I said, well, we got an x0, let's just call it xk because I'm going to put it in a loop and just keep updating xk. I'm doing the same thing here, okay? So I've got my current value of the function, and I want to figure out a move that's going to give me an xk plus 1 where the function decreases, okay? Well, I look at the local linearization of the function. Whoops, I had x over here, so I've got to keep my x. I don't change it yet. Okay. Now, I seek xk plus 1 such that f of xk plus 1 is strictly less than f of xk. Okay? I'm trying to come up with an algorithm that, given a current guess for xk, keep missing. Given my current guess, how should I choose the next one in order to achieve my goal, which is decreasing this value? Well, let's figure it out, okay? So we want f of xk plus 1 to be strictly less than f of xk, and based upon our linear approximation, well, we learn a whole lot. So what do we need? We need df by dx, the slope at the point xk, times xk plus 1 minus xk to be negative. That's the only way that we decrease. Okay, so it's just like the picture. What do I do if df by dx of xk is positive? That implies I need xk plus 1 minus xk to be negative, so I need xk plus 1 to be less than xk. Okay. If the derivative is positive, I decrease x, just like I said with the slope. But this is just coming from our linear approximation. And if df by dxk is negative, that implies I need xk plus 1 minus xk to be positive. And so I need xk plus 1 to be greater than xk. So yep, just like we saw with the picture, the linear approximation is telling us the direction we have to move in order to go towards a minima. And then, of course, if we have dx by dxk equals 0, we do not know how to move, okay? Okay, we don't know how to update. But that's not a really terrible thing because we know that this thing being 0 is a necessary condition for a local minima. So if we have that, we're going like, hallelujah, we're probably there. Well, maybe we're there. At least we have a chance we're there, and we'll have to do some extra tests. Okay, so on Wednesday, we'll have our first version of something that's called gradient descent. Because minus s df of xk dx, s greater than 0 is called the step size. Okay, so we'll just use our information about the sign of the derivative. We want to move in the opposite direction of the sign of the derivative. And then how far do we go? Well, that's going to be a parameter that we tune in our algorithm. And it will march us towards local minima. And we'll look at that. Can you imagine anything easier? Not really, okay? Not really. So that's what we're going to be doing. And I don't know, to me, I just find it so geeky that all of this stuff comes from our local linear approximations to functions, okay? Linearization, linear algebra. Thank you.